Hi, so this is lecture 2 of John's theorem and optimal design. And in this lecture, I will cover the idea of maximum volume ellipsoid, and we will see what it means for an ellipsoid to be of maximum volume that is contained inside a convex body. So we'll start with the basic definition of volume in Rn. So recall that we are dealing in Rn, the n-dimensional Euclidean space, and we have the norm, which is the Euclidean norm, right? Such that norm of x is equals summation I equals to 1 to n xi square root of all this. So we are basically equipped with this norm structure on the space, Euclidean space, and now we want to define what it means for an object to have some volume. So we will generalize the idea of volume from 1D and 2D. And so basically in one dimensional space, we have the volume of an interval. The volume of this interval A1, B1. This is nothing but the length of the interval B1 minus A1. This is also called the Lebesgue measure of this interval, right? And we will extend this definition to higher dimension. And we will say that suppose we are given a set S, which is basically the Cartesian product of n intervals, right? Then the volume of S is nothing but the product I equals to 1 to n bi minus ai. So this is the volume that we will use whenever we mean volume, and uh, like we it's a so basically this is not that this is defined for only sets which look like Cartesian products of n intervals, but the essential idea is that for any arbitrary objects in this n-dimensional space, you can approximate them with a countable union of such intervals, and therefore you can use the ideas in measure theory to say that the volume of the body is equals to the volume of the countable union of these uh, sets that look like S here. And so you can use those techniques to define the volume of any arbitrary body that can be approximated with such a set S, an arbitrary collection of, not arbitrary, I mean a countable collection of them. So therefore, like we can have volumes of any sort of regular looking objects in n dimension. And one such object that we are interested in studying is the ellipsoid. So last time we saw that an ellipsoid is given by this linear transformation plus a translation of the unit ball. So we will denote with PD the set of positive definite matrices, and B is a vector. So basically, and recall that Bn is our unit ball in n dimensions. So B plus T of Bn is basically an ellipsoid that we generated using B and T. And we want to define the volume of this E. And using some arguments that I won't go into here, you can take this as a sort of definition. But essentially, the volume of this ellipsoid is determinant of T times volume of Bn. So this volume of Bn is a like sort of fundamental volume in the n-dimensional Euclidean space. Like there is a closed form expression for this. But in our discussion, we will not go into that. We'll just take this volume of Bn as something that we can compute or know But this determinant of T is essentially the way of characterizing the volume of this ellipsoid, which comes from a transformation of the unit wall through the matrix T. So note that since T is positive definite, right? Therefore, the determinant of T is a positive quantity. So indeed, this volume of this ellipsoid is some positive quantity times the volume of the ball. And therefore, we are interested in finding the maximum volume ellipsoid that is contained in a convex body K, right? So basically, we want to solve this problem. Maximize overall E, volume of E, such that E contains K, where K is the convex body of interest, right? And so, firstly, the question is like, I mean, why would we even assume that such an ellipsoid exists, right? And if it exists, can we say further something like that such an ellipsoid is unique for every convex body? So, indeed, that is the case. So, we have our first lemma, which is that given convex body K, right, the maximum volume ellipsoid, I'll abbreviate this as max vol ellipsoid, contained in K is, so firstly it exists and is unique. What does this mean? It means that basically that if you look at all possible ellipsoids that are contained in this convex body K, right, the supremum of volume of all these ellipsoids is actually attained in this set of ellipsoids. Basically, it's like first you have to argue that the supremum is indeed achieved in the set, and secondly, we will show the uniqueness through some more arguments. Uh, and so first, let me get started with the existence part. So we'll do the proof. And the idea is to show that this set of ellipsoids that are contained in K, if you write all of them down, the set that you get, that set is in some sense compact, right? You will, and if I can show that if this set is compact, then we know that by the extreme value theorem that it's a theorem in real analysis. So we know that by this theorem that the supremum will be attained within this set. So that's our goal. But note that there's a subtle difficulty here because the set of convex, the set of ellipsoids that we are considering here actually are given by matrices which are positive definite, right? And so positive definite matrices do not contain, so they are sort of an open set because you can think that we are restricted to only positive definite. So you are allowed to pick matrices whose eigenvalues are positive. So if there is a sequence of matrices whose eigenvalues while being positive gradually tends to zero, right? Then that matrix won't be a positive definite matrix. So there is like little difficulty there, but we will get around it and we will see how. So let me start with the existence part. And the argument is fairly standard. So we will start with this set F, which is the collection of all ellipsoids. And note that these ellipsoids are parameterized by a vector B and a positive definite matrix T. Therefore, it suffices to write the set in this form. P in Rn and P is PD such that what? Such that the ellipsoid B plus T of Bn is subset of K, right? So our goal is to show that this set is compact, and uh, the easy part is to show boundedness. So we again like note that by Heinberg theorem we have that if the set is bounded and closed, then it's compact, and vice versa. So therefore we will take that route. We'll show that this set is indeed one bounded and two closed. The bounded is easy to show, and that is because the convex body itself is bounded, right? So recall that convex body is a compact set, right? The definition of convex body says that it's a compact convex set with non-empty interiors. So therefore, the convex body itself is bounded, and if the convex body is bounded, then everything contained inside it also is bounded, right? So basically, with this argument, we have that we know that K is subset of R times Bn. So this R, what is this R? R is greater than 0. R is some real, right? So basically it's saying that there is a large enough ball of radius R such that the whole of the convex body is contained in this R. This is by definition of K, right? Convex body. And therefore what we have that this implies that so B plus T of Bn is contained in this R of Vn, right? Particularly note that this on the left hand side you have B plus Tn, right? So B plus T of Bn. So this Bn x equals to 0 is a part of Bn, right? The ball contains the origin. So therefore this implies that B plus T times 0, which is B, is contained in R of Bn, which further implies that B is less than equals to R. So the Euclidean norm of B is at most R, right? So all the B's that are contained in F, calligraphic F, is actually bounded. So this is the boundedness of B. And similarly for T, what we have that, so T of X, basically pick any X, right? For any X belongs to Bn, we have T of X is nothing but T of X plus B minus B, which is less than equals to, by triangle inequality, T of X plus B plus B. And now T of X plus B, this is basically an element of the ellipsoid, right? And we know that that is bounded. So this is less than equals to R, and this is less than equals to R, which is less than equals to 2. So we have that for all X in the ball in Bn, T of X is upper bounded as 2R, right? And so what we can conclude is that the operator norm, so this is also the definition of the operator norm. If we look at the definition of operator norm, it says it's the maximum of norm of Tx where X belongs to the ball, right? So this implies that T of operator norm of T is less than 2R, right? So we have shown two things. One is the Euclidean norm of all B, small b, that lies in the set F is bounded, and the operator norm of all T, which lies in the set calligraphic F, is bounded. So with this, we can conclude that F is bounded, right? The tricky part is to show that F is closed. And for that, we will use the idea of breaking these ellipsoids into two sets. So we'll split F into two sets. And the way to do that is first note that this convex body K is a has a non-empty interior, right? And what we saw in the last lecture is that it means that there is a point inside this convex body around which there exists some epsilon for which the open ball around this point is contained wholly inside the convex body. So basically it says that mathematically there exists some epsilon greater than 0 such that some epsilon greater than 0. So let me restart it this way. There exists some point y in the convex body such that for this point y there exists epsilon greater than 0 such that the ball of radius epsilon around this point y, which we wrote last time as p and y comma epsilon, right? This is contained inside the set K. So this can also be written as all x belongs to Rn such that norm of x minus y is less than epsilon. This is contained inside K, right? And therefore, what we can say is that if we look at the following set, this is our set F epsilon, and this epsilon is same as the epsilon here, right? F epsilon is the set of points like b comma t. It's a restriction of F in the following way, such that we have volume of b plus t bn is greater than equals epsilon n power epsilon power n times volume of bn. So why write it this way? Note that this ball b and y of y comma epsilon. The other way of writing this ball is same as y plus epsilon times bn, right? And what is the volume of this ellipsoid? The volume of y plus epsilon bn, and epsilon bn is nothing but your epsilon in times bn, where in is the identity matrix, right? So this is the volume, and this will be given by what we saw is the volume of ellipsoids, right? This is the formula for volume of ellipsoids, and therefore volume of this object is given as epsilon n. So it's, let me break it down. So it's determinant of epsilon in times volume of bn, and this is nothing but epsilon power n volume of b. So what we have done is we know that there exists some point y in this set K, and such that the epsilon ball around y is contained inside this set, and therefore we have taken that set and considered the all ellipses whose volume is at least this much, right? And therefore, like, the claim is that this f epsilon is actually a compact set, and the problem that we were running into, right, if all the eigenvalues tend to 0, then how do you say that it's still a compact set? Because that limit point, which is uh, not a positive definite matrix anymore, is in this set, right? So we have bypassed that problem by splitting the set F into two parts, F epsilon and the rest. The rest contains all ellipsoids of volume smaller than epsilon, and F epsilon contains all ellipsoids of volume at least epsilon n, epsilon power n times volume of Bn. And this way, like, we will now operate on F of epsilon, and later on we will see that Once we have the maximum volume ellipsoid on f of epsilon, and we have maximum volume ellipsoid on the rest of the set, since we know the rest of the set has volume less than epsilon power n times volume of Bn, so the maximum must lie in the set f epsilon, right? So formally we can state it this way. So imagine there's a sequence Bm Tn, right? This is a sequence of B and T that tends to uh, B comma T. And this tends basically means that the norm of B minus Bm uh, goes to 0 and T minus Tm goes to 0 in the operator mode, right? And therefore, now what we can say about this? This is, so let's look at a point x belongs to the ball. What happens to Bm plus Tm of x? So this quantity minus B plus T of x. Let's look at the norm of this. So this is less than equals to, first, let me write it this way. That's Bm minus B plus Tm minus T times x, right? And therefore, this is less than equals to by triangle inequality. Bm minus B plus norm of Tm minus T into x. And this is again less than equals to Bm plus B, sorry, Bm minus B plus operator norm of Tm minus T times norm of x. And we know that x belongs to the ball, right? So therefore, norm of x is at most 1. And therefore, we have Bm minus B plus Tm minus T of op, right? And note that both of them tend to 0, right? This goes to 0, this goes to 0. So therefore, can write that this goes to 0. Therefore, we are fine, right? So what we have shown is that basically that Bm plus Tm of x goes to B of T of x for all x in the ball. So basically, the ellipsoid Bm plus Tm times ball n, that goes to B plus T of ball n. So, and this happens pointwise. So if you look at a sequence of points on this sequence Bm plus Tm of ball n, then those points actually sequentially converge to the corresponding point on the ellipsoid given by B plus T of Bn. And therefore, what we have is that we can now argue that suppose, like towards a contradiction, suppose there exists x dash belongs to Bn such that B of Tx dash does not lie in K, right? This is basically saying that suppose B plus T of x dash is outside the set, and then that would mean that the ellipsoid given by B of B plus T of Bn is not in the set K, right? Like certain parts of it is outside set K, therefore it is not contained in K. So we'll show a contradiction and therefore conclude that this condition cannot happen, and therefore all of B plus T Bn lies inside the set K. And that will give us the closeness that we were seeking, because B plus B comma T is the limit point of the sequence Bm comma Tm, and therefore if we can show that B comma T also lies in the set f of epsilon, therefore we have the closeness, right? So suppose this happens, so what this means, that it means that there exists a small neighborhood of B plus Tx dash, right? So this means there exists an epsilon dash, there exists epsilon dash greater than 0, such that this is not contained, this is wholly outside K. So this is in Rn minus. So it lies completely outside. So imagine this, basically the diagram is, so you have the convex body, something like this, and you have an ellipsoid that slightly goes outside, right? Then you would have a point here, sorry, you would have a point here whose epsilon ball, right? There exists a small ball around this point such that that whole ball lies outside the convex set. So therefore, we have that. So if the first condition holds, then second condition holds. And the essential thing to note here is that the points bm plus tm of x dash still converges to b plus t of x dash, right? And we have that this bm plus tm x dash always lies within the convex body because we picked the set bm, the sequence bm comma tm to lie in. So this is a sequence in f epsilon, right? And f epsilon contains all such b comma t which are completely inside the convex body, right? So this bm plus tm, this is always in the convex body k, but we know that this is not in the convex body. And how can that happen? That actually cannot happen because the convergence says that whatever epsilon dash you pick, right? So even for this given epsilon dash that we have, right? It, so convergence implies given epsilon dash greater than 0, there exists some m belongs to natural numbers such that for all m greater than m, right, the distance between b plus tm of x dash and b of t plus x dash, this will be less than epsilon dash, right? This is the convergence statement. And I know that this is a point in K, call this point P. So P belongs to K, right? And this P lies at a distance less than epsilon dash from this point, right? So basically, this implies that P lies in the ball P plus T x dash comma epsilon dash. So we have two things now. Therefore, P lies in K and P lies in this ball. This implies that K intersection B of n B plus Tx dash comma epsilon dash is not equals to 5. But what did we assume? We assumed that this ball is actually completely outside K, right? And specifically, we assume that this ball has no intersection with K, right? But we have shown here that there is actually a point that has lies in the intersection of K and this ball. So it's a contradiction, right? And therefore, we have that this implies that there exists no T dash, there exists no X dash belongs to Bn such that B plus Tx dash does not belongs to K. In other words, the ellipsoid B plus T of Bn is subset of K. So we have shown that, and moreover, note that the volume, what is the volume of this ellipsoid? The volume of this ellipsoid is determinant of T, right, times vol of Vn. And determinant is a continuous map. So by continuity of this determinant and the fact that Tm converges to T and continuity of determinant function, we have that determinant of Tm will converge to determinant of T, right? So therefore, and note that all of these are at least epsilon power n. So this will also be at least epsilon power n by convergence and continuity. So therefore, what we have shown is that B comma T indeed lies in the set F epsilon, because two things. One, this ellipsoid is contained in the convex body K, and its volume is at least epsilon power n times volume of the ball, right? So therefore, it concludes that F epsilon is closed. So if F epsilon is closed, then we know that there is a maximum element in F epsilon. So by basically closed and bounded F epsilon, we conclude F epsilon is compact. This therefore implies that maximum is achieved in this in F epsilon. Specifically, there exists, so this means that there exists epsilon, like some ellipsoid equals to B star comma T star belongs to F epsilon, such that volume of this B star plus T star Bn is greater than equals to volume of B plus T of Bn for all B comma T greater than F of epsilon belongs to F of epsilon. So this shows that this happens, and what we know is that all ellipsoids in this set F of epsilon has volume at least epsilon power n times volume of Bn. Therefore, volume of this B star plus T star times Bn is at least epsilon power n times volume of Bn. And let's now look at the complementary set F minus of F of epsilon, right? On this complementary set, what we have? We have the volume of all ellipsoids. So imagine B dash T dash belonging to this. Then volume of B dash plus T dash Bn is strictly less than epsilon times volume of B. So therefore, this B star T star is indeed the maximum volume ellipsoid that is contained inside K, right? So this concludes the existence